Alright guys, so we're going to talk about the intermediate values theorem. One of your classmates made me aware of the fact that I did not record a video for this section and it's a bit confusing. So I will go ahead and record it on my computer, which is not as nice as the light board, but it's what we have. It's a Friday night, so whatever. That's how exciting my life is, you see. Friday night I'm recording videos for you guys. Hey, that's exciting. Anyways, let's try to motivate this theorem. So let's say that we have a function in between an interval, a closed interval, a to b. And let's say that the function happens to be, let's use color, because colors are always great. So we have our function. Let's say that the function is continuous and it's going to be, in this case, increasing. It doesn't have to be increasing, but let's say it's increasing. Right here we're going to have the image of a, so f of a. That was a straight line, yeah, this one is f of b. So that's b, so here we have f of b. And we're going to have a value, sorry about that. We're going to have a value k, let's call it, in between f of a and f of b. That's a bit thick. Do I have a thinner one? Yes, I do. Alright, that explains. So what the theorem will tell us is that if the function is continuous and I have a k that is in between f of a and f of b, there will be a value c for which k is equal to f of c. So before we write it formally, I mean, this is almost what we're saying is that if the line is continuous and it goes below and above a point, at some point it has to cross through the point. That's really what the theorem is saying. But how could it fail, you say? Well, let's take a look at what happens when the function is not continuous. So let's say, how would it fail? So I'm going to grab my function here, and I'm going to pick same kind of situation, a to b. And then I'm going to say, okay, I have a value of f of a, so I'm going to say that this one starts, now I grab my colors, I'll say that this one starts here. So that's going to be my f of a. And to continue with what our idea was, we had increasing, so I'm going to put here f of b. And you notice I haven't drawn the graph of the function itself, and there's a reason for it. I want to make it fail. So I'm going to say that k will be somewhere in between those two guys, so I'm going to put it here. I'm going to put k, okay? And you say, well, the function goes from here to here, at some point has to go through and intersect this line y equals k, right? Makes sense, correct? Sure, why not? Let's make it fail. So we stop here and take a little jump and keep going. And that function right there is not continuous at this value. Let's call it c in this case. It's not continuous there, and it jumps through, and then I don't have a guarantee that my function is taking the value of k at all. But if the function is continuous, that jump cannot happen, and the function is guaranteed to take that value of k. Alright, so let's go ahead and state the theorem, and then we will do a couple examples for it. Okay, so I went ahead and wrote the theorem. So let's read it. Let f be a function defined on the interval a to b. We don't care about what happens to a function outside. It could very well be defined outside. That's fine. If f is continuous on the interval a to b, so you are ruling this situation out. It has to be continuous. And k is a number in between f of a and f of b, meaning k is somewhere in between these two numbers. Now remember that with this function is increasing, so f of a is less than f of b, but it doesn't mean that it cannot be decreasing. In fact, the function could just do a couple different movements and have f of a being here, f of b being here, and then k would have to be somewhere in between that. That's fine. But And if it's equal, then k has to be equal to f of a and f of b. That's not very interesting, as I said before. But if that is the case, if k is a number between f of a and f of b, then there exists a number c on the interval ab. That's this guy here. That will go ahead and take the value. So f of c is going to be equal to k. Now, does that mean there's a unique element or a unique c? No, absolutely not. So you could have the function do one of these things, and then k could be somewhere here, and you can have more than one value. So this could be one of the c's, this could be another one, and this could be another one. So I guess C1, C2, C3. The theorem only guarantees that there exists at least one. There could be more, of course. It doesn't mean that it's just going to be one. All right. So let's go ahead and look at some applications of this theorem. All right. So this is a very typical example of the intermediate value theorem. So that helps you determine an interval, or that the function has a zero on an interval. So what happens is this function here is a polynomial function. So firstly, the function is continuous everywhere on the real line. So since the function f is a polynomial, it is continuous. It's continuous on the entire real line, but in particular, it is continuous on the interval 0 to 1. Why do I care about that? Why do I make that a point? Well, because I need that for my intermediate value theorem to apply. Then I'm going to say, note that f of 0, when you plug it in, you get 0 for this one, minus 2 times 0 is 0, minus 0, all that is 0, plus 1 is going to be f of 0 equals 1. And f of 1, we can evaluate. If you want to pause the video and put it in, it's very easy. So 1 minus 2 is negative 1, minus 1 is negative 2, plus 1 is negative 1. Okay, so what is happening before I write the conclusion, because that would be unfair if you don't see what's happening. It's kind of nice to see it in a little graph. We have that at x equals 0, the function is taking the value of 1. I don't know what else happens, but I know then when we go to 1, the function takes the value of negative 1. The function is continuous. I don't know where, but somewhere in between here, the function will cross through 0, through the x-axis. So that's what the intermediate value theorem is guaranteeing. So since 0 is in, that's what we're looking for, the zeros, right? Is in the interval from negative 1 to 1, we know, or the intermediate value theorem, let's call it IVT for short, guarantees or gives the existence, I suppose guarantees was easier to write, the existence, let's move over here, and I have to, of some value c, of c in the interval between 0 and 1. So what that is telling me is that on this interval here, between 0 and 1, there will be a c, that is the guy that I drew here, that for which f of c is equal to 0. All right, over here, f of c is equal to 0. So I'm guaranteed the existence of at least one 0. Could the function have oscillated around and then gone back here? Sure, I don't know. I do know because I drew the graph on decimals before I started the problem, but you know, the theorem just guarantees there's at least one. Alright, so that's that for this video, guys. It's a short video because As I said, it's Friday night, so I've just ran to the office to record it real quick. All right, so I hope you guys have a great weekend, and I'll see you next week.